Singular value decomposition. In this lesson, we review singular value decomposition, a generalization of the spectral theorem to not only nonsymmetric but also nonsquare matrices. In the previous lessons we saw that a matrix maps a circle to an ellipse, that the determinant tells us the change in area, and that eigenvalues tell us the amount of stretch along some invariant directions. In this lesson we will find the vectors that become the principal axis of the ellipsoid and, loosely speaking, the maximum amount of stretch and squash. This gives us useful information on characterizing and approximating high-dimensional matrices. In the previous lesson, we saw that the maximum and minimum amount of stretch on a symmetric matrix is along the eigenvectors. Since the eigenvalues may be negative, the orientation may change. By requiring all eigenvalues to be positive, we preserve orientation. If a matrix is symmetric and all its eigenvalues are positive, we say that the matrix is positive definite. If we also allow zero eigenvalues, we say that the matrix is positive semi-definite. A positive definite matrix A has the decomposition A equals Q lambda Q transpose, where Q is an orthogonal matrix of eigenvectors, and lambda is a diagonal matrix of positive eigenvalues. For example, the matrix 2, 1, 1, 2 has this decomposition which says rotate, stretch, and rotate back. So, we see that a positive definite matrix maps a circle to an ellipse merely by stretching. Remarkably enough, this idea rotate, stretch, rotate is applicable to all matrices, even matrices that are not square. In general, a matrix A equals an orthogonal matrix U times a diagonal matrix sigma times a second orthogonal matrix V transpose. This is called the singular value decomposition, or SVD. Let's determine the values of U, sigma and V. To find these matrices, we multiply A on the left by A transpose. This gives us a positive semi-definite matrix. The resulting right-hand side can be simplified, and because U is an orthogonal matrix, U transpose U cancels, which simplifies the right-hand side even more, leaving us with the diagonalization of A transpose A. Sigma transpose sigma is the square diagonal eigenvalue matrix for a transpose A. The diagonal elements of sigma are called the singular values of the matrix A, and are equal to the square root of the eigenvalues of A transpose A. Correspondingly, V is the eigenvector matrix of A transpose A. We still need U. Let's go back to the singular value decomposition A equals U sigma V transpose. We right multiply this equation by A transpose, and simplify the resulting expression. Because V is an orthogonal matrix, we can cancel the V transpose V term, leaving us with the diagonalization of A transpose. Therefore, U is the orthogonal matrix of eigenvectors for A transpose. Let's summarize the singular value decomposition. U is an orthogonal matrix of eigenvectors of A transpose A. Sigma is a rectangular diagonal matrix. The diagonal elements are called the singular values of A, and are equal to the square root of the eigenvalues of A transpose A. By rearranging the columns of U, we can always order the singular values from largest to smallest. Finally, V is an orthogonal matrix of eigenvectors of A transpose. Let's see the SVD in action. We'll take the matrix 2, 2, minus 1, 2 to demonstrate. Here is its SVD. V transpose first rotates the sheet by approximately 63 degrees counterclockwise. Sigma then stretches the sheet by 3 in the X direction and by 2 in the Y direction. Finally, U rotates the sheet by approximately 27 degrees clockwise. Another way of think about this is to say that the matrix A maps the orthogonal columns vectors of V to the column vectors of U, with lengths given by the respective singular values. Matrices can sometimes be almost singular if the columns are almost linearly dependent. Such matrices pose difficulties for numerical computation. Consider this matrix. The matrix has singular values of approximately 2.05 and 0.05, mapping the circle into a very narrow ellipse. The smallest singular value does not contribute much information, and as an approximation, we can zero it out. The ellipse is now projected into a one-dimensional subspace. Since the leftmost columns of U and V no longer contribute any information, we may eliminate them to construct an economy version SVD. This approximation gives us the best rank 1 matrix approximation to the original matrix. Let's examine a more interesting matrix. Suppose we take a 100 by 100 pixel image as a matrix whose elements equal to the color intensities. Since there is structure to the picture, there is a lot of correlation between the columns. This means that the columns are close to being linearly dependent. Equivalently, the correlation matrix AA transpose is almost singular, which means that there are a lot of singular values close to zero. Here's a plot of the singular values of the matrix. The largest singular value is much larger than any of the others because of the bias in the data. The image is predominantly white. Let's examine the other singular values. The large singular values contribute the most information about the matrix. Roughly half of the singular values contribute very little information. The rank of the matrix is more or less 50. Compare the singular values of the structured image of the sheep to singular values of a random matrix. The value of the elements of the random matrix were with the same mean and standard deviation as that of the sheep. Even the 100 singular value of the random matrix contributes significant information. On the other hand, we can project the image of the sheep into a substantially lower dimensional subspace and still retain important qualitative features of the image. Let's take a look. I've only kept the largest singular value. The image is now a rank 1 matrix. This time we keep the largest 2 singular values. As more singular values are included, notice how the image of the sheep is rebuilt. Here's a rank 10 approximation. The image is clearly a sheep. Let's jump up to rank 20. And now let's look at rank 30. While there is change from rank 20 to rank 30, the change is rather minor. As you can see, a rank 100 matrix can be described by a much lower rank approximation.